Now let's look at a few examples which illustrate some big problems with the internal rate of return approach. Issue number 1, non-conventional cash flows. So a project with conventional cash flows is the one in which we would need to invest money today and in return receive profits over the next several number of years. A non-conventional project is the one where we have a cash inflow today followed by cash outflows in the future. So everything is backwards. These type of non-conventional projects are also known as financing type projects as opposed to investing type. And the word financing corresponds to financing something, like taking a loan, borrowing money. Because when you take a loan, the loan amount that you receive is a cash inflow today. And in the future years, you will be slowly paying your loan amount off. So you have cash outflows in the future. So it's exactly the opposite of what you see in an investing type project. So let's look at pretty much the same problem we had on one of the earlier slides. The one that was used to explain the whole IRR approach. The only thing we are doing differently, we are switching the signs. So now in year 0, you would be receiving $10. In years 1, 2, 3, and 4, you would be paying $6, $5, $8, and $8, respectively. So I kept the dollar amounts the same, but I switched the signs. In which case should we accept or reject this project? So let's approach it the same way as the identical problem with the switched signs. Let's try randomly a few discount rates. The same ones we tried before, 30%, 50%, and 70%. And let's right away plot our resulting net present values on the same graph that we used earlier, with the discount rate along the horizontal axis and the net present value along the vertical axis. So when we try the discount rates of 30%, then 50%, then 70%, and for each compute the net present value using, for example, the cash flow case, you would get the same NPVs as we had before, but with the opposite signs. So at the 30% discount rate, the net present value is negative $4.02. At 50% discount rate, the net present value is negative 17 cents. And at the highest 70% discount rate, the net present value is positive $2.15. So we can draw a smooth curve going through these 3 points, and that's our net present value profile. However, here it's an upward sloping line, right? So everything is like an upside down mirror image of what we had before. An interesting thing is that the IRR in this case is the same as before, 51.2%. You can also check it in the financial calculator, right? So the IRR itself has not changed. So what has changed? What has changed is in which range of the required return we are going to say accept the project, and for which range we're going to say reject the project. Everything is now reversed. We are rejecting the project whenever the required return is below the IRR. That's the opposite of what the traditional IRR rule says. And we reject the project when the required return is below the IRR, because that's where the net present value is less than $0, right? Graphically, the NPV profile, the NPV line, is below the horizontal axis. And the project would be accepted if the required return is above our internal rate of return. So again, that's the opposite of what the traditional IRR rule for a traditional investment type project would say. So to review, what we mean by conventional project is the one where you invest money today and then wait to receive your profits over a number of future years. So it's an investing type project. An example of a project with non-conventional cash flows is the one that has a cash inflow today followed by cash outflows in the future. And an example of that would be taking a loan. That's where the name financing type project comes from. If you compare the graphical relationship between the discount rate and the net present value, we get sort of a mirror image for the financing type project. For the investing type project, the net present value profile is sloping down and to the right. For financing type projects, the net present value profile slopes up and to the right. So in the first case, the relationship between the discount rate and the net present value is negative. In the second case, it's positive. And for a conventional investing type project, we would say accept the project if the required return is less than the internal rate of return. Instead, for financing type projects, we would accept the project if the required return is above the internal rate of return. And so the traditional IRR rule does not work when we deal with financing type projects. That's the conclusion. And like we already had on the last couple of slides, the new rule should be rewritten completely and say something like accept the project if the IRR is less than the required return, and reject the project if the IRR is greater than the required return. Let's look at the second issue with the internal rate of return approach. This is another example of non-conventional cash flows in a project. And what's going on here is cash flows change signs more than once. So think about the following example. It's a 2-year project. In year 0, you invest $60. In year 1, you receive $155. But in year 2, you again need to spend a lot of money, and the cash flows then is negative 100. Here, the cash flows change signs 2 times. From negative to positive when we go from year 0 to year 1, and then again from positive to negative when we go from year 1 to year 2. What happens in this case is when you, again try a few different discount rates, plug them into the net present value formula or the cash flow keys in the calculator and find the IRR, and then when you connect a few results that you would get a curve, but the unusual thing about it is that it crosses the horizontal axis in 2 places, right? So there is no one IRR when cash flows change signs twice. There are 2 IRRs when cash flows change signs twice. And the IRRs in this particular example are 25% and 33.33%. By the way, if you try this in the financial calculator, let's do it together. Let me move it here. Second plus minus enter. I've just cleared everything. Cash flow key, 60 negative enter, down. 155, enter, down, down. 100, negative, enter, down, down. IRR, compute. What does the display say? It says IRR equals 25%. That's the first IRR. Does the financial calculator tell us what the second IRR is? No, it cannot do it. It only shows the first one of the two, but you know that there should be two. So the financial calculator is kind of, unable to handle this kind of complex problems. And for the purpose of this class, you're never going to be asked to do numerical problems like this, in which you need to find both IRRs. The only thing you should know is, in general, when cash flows switch signs twice, there will be two IRRs. And in this particular example, and in this particular example, what's going to happen is something pretty complicated. There is one range of discount rates for which the net present value is positive, and that allows us to say accept the project. That's when the discount rate is between the two internal rates of return, between 25% and 33.33%, the second IRR. And there are two ranges of the discount rate for which the project should be rejected. That's if the required return is below the first IRR, so less than 25%, or if the required return is greater than the second IRR, greater than 33.33%. So again, the traditional IRR rule does not work at all. It's something a lot more complicated. So the entire rule has to be rewritten. And guess what? Let's look at another example here, side by side. I'm keeping the same dollar amounts, but I'm switching their signs. So in year 0, the cash flow is 60. That's a cash inflow. In year 1, the cash flow is 155, but this time it's negative, a cash outflow. And then in year 2 in the future, the cash flow from this project is $100, and it's positive, a cash inflow. So I kept the dollar amounts the same as in my first example on the slide, but I switched the signs. And so it kind of became what we call a financing type project, right? Which is already what we call a non-conventional type project. And on top of that, we have another interesting thing going on. The signs, the cash flows change signs 2 times, from positive to negative, going from year 0 to year 1. And then for the second time, from negative to positive, going from year 1 to year 2. So if you spend a little bit of time to, try a few discount rates and for each calculate the net present value for these cash flows, you would again get a curve that crosses the horizontal axis in 2 places. So once again, there are 2 IRRs, and they happen to be, again, which is not a coincidence, the same 25% and 33.33%, like with the first example on this slide. The only thing that changed is the entire NPV profile, the NPV line, is now flipped upside down. Now it goes down and then back up, rather than up and then down. And as a result of this sort of transformation, in the sort of graphical illustration of what's going on, as a result of that, the range of the discount rate of the required return that makes the project worth accepting is now, there are actually two ranges now. Below the first IRR, below 25%, and above the second IRR, above 33.33%. And between the IRRs is where the project would be rejected. So the project would be rejected between 25% and 33.33% for the required return, because the net present value in this case is below $0, right? So these two examples side by side illustrate this second issue with the internal rate of return approach. When we have something strange or non-conventional going on, like cash flows changing signs more than once, then we're gonna get multiple IRRs, and the traditional IRR rule stops working. In these both little examples, if you try to use the financial calculator, it will only give you the second one of the two IRRs. Turns out that if in a numerical problem the cash flows change signs 3 times, there will be 3 IRRs. If the cash flows change signs 100 times, there will be 100 IRRs. So the NPV line would be crossing the horizontal axis over and over and over again, kind of look like a wave. So things get even more complicated with the whole accept and reject regions.